In this video, we're going to have a look at fractals. A fractal is an infinitely repeating pattern. They are created by repeating a simple process over and over. This repeated process is called an iteration. Nature is full of fractals in trees, rivers, coastlines, even seashells. The cross-section of a stalk of broccoli shows fractal branching into florets. We say that these shapes are self-similar. We can see the branch branching, and then the smaller branch branching, and then if you look closely, the pattern continues. Simple fractals are constructed by iteration. For example, if we start with one triangle filled in, and then remove the middle quarter, and repeat this pattern, we have 3 iterations. Here we see iteration 1, 2, and 3. Let's let n equal the iteration number. That is n equals 1, n equals 2, and n equals 3. The self-similar shapes are the shaded triangles. The number of self-similar shapes forms a pattern. Let's call the number of self-similar shapes S. In the first iteration, we have 1 self-similar shape. In the second iteration, we have 3. And the third iteration, we have 9. This sequence is known as a geometric sequence. As each term after the first is found by multiplying the previous by a constant number called a common ratio. In this sequence, you can see that the common ratio is 3, as each term is a multiple of 3 times the previous. The rule for finding a term, or in our case an iteration, is a times r to the power of n minus 1, where a equals the first term and r equals the common ratio. Coming back to our example, here s, the number of shapes, equals the first term 1 times the common ratio r, 3, to the power of n minus 1. Now 1 times 3 to the power of n minus 1 can just be simplified to s equals 3 to the n minus 1. Suppose we take a square of side lengths 1 unit and divide it into quarters and remove one of the diagonals. We then repeat this process. Iteration 1 has 2 self-similar shapes, being the shaded squares. Iteration 2 has 4 self-similar shapes. And iteration 3, you can see, has 8 self-similar shapes. The area of each single self-similar shapes can be found by just looking at the fraction of the total square. The area in iteration 1 of one self-similar shape is 1/4. The area of a single similar shape in iteration 2 is 1/4 of the quarter, that is 1/16. And the area of one self-similar shape in iteration 3 is 1/4 of the previous, or 1/16, which is 1/64. The total area, let's call it A, can then be found by multiplying the number of self-similar shapes by the area of a single self-similar shape. In iteration 1, we had 2 that are both 1/4. 2 times 1/4 is therefore 1/2. In iteration 2, we had 4 self-similar shapes, with each area being 1/16. 4 times 1/16 is simplified to 1/4. And in the third iteration, we had 8 self-similar shapes, each being 1/64 in size. Therefore, 8 times 1 over 64 simplifies to 1/8. You can see that the common ratio in this example is 1/2. 1/2 times 1/2 is 1/4, and 1/4 times 1/2 is 1/8. Therefore, the rule for this pattern, let's say A, the total area, is the value of the first term 1/2 times the common ratio, which is 1/2, to the power of n minus 1. This simplifies using our index laws. When we multiply a number with the same base, being a half, we add the powers. And we can see this first half being a power of a 1. 1/2 plus n minus 1 is simply a to the power of 1/2. A equals 1/2 to the power of n. When we look at the geometric sequence rule, n minus 1, we have to subtract 1 because we're allowing for the first term in our rule. So if this infinitely repeating pattern continues n times, the rule is the first term times the common ratio to the power of n minus 1. And there's a very quick summary on fractals.